What if a metal could sacrifice itself just to save another? This is zinc.
We usually think of engineering as this, massive war against nature.
Well, absolutely. It's humanity versus the elements.
Right. Like when we build these huge things, suspension bridges, skyscrapers, cargo ships, the whole goal is invincibility.
Yeah, you want materials that are just impossibly tough. Things that absolutely refuse to break under pressure.
Because historically, right, structural failure means catastrophic loss. So the philosophy has always been about permanence.
Right, you build a barrier so strong that the environment just, well, it can't get through it.
But the stack of notes and research we're looking at for today's deep dive completely upends that entire philosophy.
It really does. It's such a fascinating pivot.
We're diving into element 30, zinc.
Yes. Good old ZN on the periodic table.
Because this metal, it protects our most vital infrastructure, but not by being indestructible. It protects things by deliberately getting destroyed.
Which is, it's just a masterclass in material science when you really look at it.
It's an engineering solution built entirely around calculated sacrifice. And I just have to ask right at the top, how can a metal protect another metal by getting destroyed itself?
Well, it's one of the most brilliant solutions to a massive engineering problem. When you look closely at the electrochemistry involved here, you realize that without this one specific element quietly taking the hit in the background, our modern world would quite literally crumble.
Okay, let's unpack this, because before we can understand why zinc makes that sacrifice, we really need to look at the victim in this scenario.
Right, the material we build everything out of, steel.
Exactly. Now, we all know that iron and steel oxidize when they're exposed to moisture and oxygen.
We've all seen rust.
Yeah, but looking at the sheer scale of the data here, it's clear that rust isn't just like some cosmetic surface blemish. It's an aggressive structural rot.
Oh, it's devastating. This raises an important question about how we view rust. We really need to move past the idea of it just being, an ugly brown spot on a car fender.
Right, like it's just a paint issue.
Exactly. When iron oxidizes, it undergoes this profound molecular transformation. The iron atoms bond with oxygen to form iron oxide. And here is the fatal flaw for engineering iron oxide is physically larger than the iron it just replaced.
Right, really? It actually gets bigger.
Yeah, up to 6 times larger in volume.
Oh, wow. So it's essentially expanding from the inside out.
Precisely. The crystalline structure of the metal is just completely breaking down.
Yeah.
Because the rust expands. It creates this immense internal stress.
Like a slow-motion invisible fire that's literally burning away the structural integrity of the steel.
That's a great way to put it. It flakes off. Engineers call it spalling, which immediately exposes the fresh, vulnerable iron underneath to the exact same attack.
So it keeps eating away at it.
It's a relentless, self-perpetuating cycle. If a suspension bridge, or say the internal I-beams of a skyscraper start oxidizing, you aren't just losing the surface.
You're losing the actual geometry that holds the building up.
Exactly. And the economic footprint of that destruction is just staggering.
Yeah, the sources indicate corrosion costs the global economy trillions of dollars annually. Trillions, with a T.
It's a massive, massive problem.
So engineers were basically trapped. They desperately needed steel because of its flexibility and its load-bearing strength. But the atmosphere itself is constantly trying to burn it down.
Which brings us to the necessity of an intervention. You can't change the atmosphere.
No, we need oxygen to breathe, unfortunately.
All right, so you have to change how the steel interacts with it. And that brings us to element 30.
Zinc. Now, if you look at pure zinc, it's this bluish-white, somewhat brittle metal. It doesn't exactly scream, superhero.
No, it's not terribly impressive on its own.
It's not super hard like titanium, and it isn't highly unreactive like gold. In fact, its extreme reactivity is exactly why it was chosen for this job.
That is the beautiful paradox of zinc. Its chemical properties, specifically its standard electrode potential, make it the absolute perfect candidate to step in front of that slow-motion fire.
Right. And this is done through galvanization.
Exactly.
And standard galvanization, like hot dip galvanizing, where they chemically clean fabricated steel and just submerge it in a vat of molten zinc at around 850 degrees Fahrenheit. It seems pretty straightforward at first glance.
They're basically giving the steel a zinc jacket.
Right. But if it were just a physical barrier, like a coat of paint, any scratch would be a death sentence for the steel underneath.
That's the key distinction. Paint is a passive barrier.
Passive, right.
If you drag a key across a painted car door, right down to the bare metal, Oxidation begins instantly at that scratch.
Because the seal is broken.
Exactly. And worse, the moisture will creep under the edges of the paint, oxidizing the metal from the inside out. It bubbles the paint off. The protection is dead.
Wait, so you're telling me that zinc isn't just a physical wall, it's like an active participant?
What's fascinating here is that zinc provides what's known as sacrificial protection, or cathodic protection.
So it actually wants to take the hit, but how does getting destroyed actually help the structure survive?
Well, let's look at the mechanics of it. In chemistry, different metals have different electronegativities, basically different tendencies to hold onto their electrons.
Okay.
Zinc has a much lower standard reduction potential than iron, which is just a fancy way of saying zinc is far more willing to give up its electrons than iron is.
Okay, so when oxygen and moisture arrive on the scene, which is basically an electrochemical attack looking to steal electrons, the zinc just intercepts the attack.
Exactly. It acts as a decoy.
Yeah.
When zinc and iron are electrically connected, like they are in galvanized steel, they form a galvanic cell.
Like a battery.
Basically, yeah. The zinc acts as the anode, and the steel becomes the cathode. The oxygen pulls electrons, and because zinc is more reactive, it gladly surrenders its electrons first.
Oh, wow.
The zinc oxidizes, and the steel remains completely structurally intact. It's a deliberate engineering choice to let the zinc take the damage.
And this is where the mechanism gets truly wild for me. If I take a grinder and carve a deep gash into a galvanized steel pipe exposing the raw iron underneath, the flame motion fire doesn't start in that gap.
No, it doesn't.
The zinc surrounding the gash continues to protect the exposed steel. How is that possible if it's not even touching it?
Because as long as there is even a thin film of moisture present.
Which acts as an electrolyte, right?
Exactly. It acts as an electrolyte to conduct the ions. The electrons will actually flow from the surrounding zinc through the steel to the exposed area.
That is incredible.
The zinc literally sacrifices its own atomic structure, just weathering away over the years, specifically to supply the electrons that the oxygen is demanding.
So it satiates the environment's hunger for electrons so the steel doesn't have to?
Precisely.
It's a calculated redirection of the attack. You build a system that explicitly plans for destruction, but you dictate exactly what gets destroyed.
It's engineering at its finest.
Now, thinking about the sheer scale of this, every highway guardrail, street lamp, suspension bridge, we must be consuming just an astronomical amount of zinc.
Oh, massive amounts.
So what does this all mean for where we get it? Because I know pure zinc isn't just lying around on the forest floor waiting to be picked up.
No, definitely not. Like most reactive metals, it's locked away deep in the Earth's crust, tightly bound to other elements.
Right.
The most commercially significant zinc mineral is called sphalerite, which is primarily zinc sulfide.
Okay, so logically, if zinc is this highly reactive metal that just loves to throw its electrons around, tearing it away from sulfur must be incredibly energy intensive.
You're spot on. You can't just melt it out of a rock over a campfire. Extracting zinc from sphalerite is a massive industrial undertaking.
How do they even do it?
Well, first you have to concentrate the ore and then subject it to what's called roasting. You blast the zinc sulfide with oxygen at extreme temperatures to convert it into zinc oxide.
Which releases sulfur dioxide in the process, I imagine.
It does. And even then, after all that, you still just have zinc oxide.
You still have to strip the oxygen away to get the pure element.
Right. From there, you typically use something called electrowinning. You dissolve the zinc oxide in sulfuric acid to create a zinc sulfate solution.
Sounds intense.
It is. And then you run a massive electrical current through it to force the pure zinc metal to plate out onto cathodes.
Or I saw in the notes, there's another way. Pyrometallurgy.
Yeah, pyrometallurgy. That involves intense heat and carbon to produce the zinc oxide, but both methods require just an immense amount of energy.
It really puts into perspective how vital this metal is. We expend massive amounts of energy to rip this rock out of the ground, refine it, just so it can slowly weather away on the side of a bridge.
It's the cost of modern civilization.
But, you know, galvanization isn't its only industrial role. The notes show that this rock, pulled from the ground, ends up in materials we interact with constantly.
Oh, absolutely. Zinc is everywhere.
Like brass, for instance.
Yes. Humans were using zinc to make brass centuries before we had any formal understanding of atomic structures or standard reduction potentials.
Because copper on its own is, well, it's highly conductive, but it's relatively soft, right? It's easily bent.
Yeah, exactly. So by alloying it with zinc, you are fundamentally changing the crystalline lattice of the metal.
Wait, how does that work?
When you melt copper and zinc together, the zinc atoms actually substitute for copper atoms in the crystal lattice.
Oh, I see.
And because the zinc atoms are slightly different in size, they distort the lattice just enough to create internal resistance to deformation.
So it locks it up.
Precisely. You end up with brass,
Yeah.
a material that is significantly harder, highly machinable, and incredibly resistant to corrosion. Every brass plumbing fixture, door handle, or acoustic instrument relies on that specific atomic substitution.
That's amazing. And because of that exact same electron donating property we talked about with the bridge protection, zinc is also the backbone of everyday portable power.
Batteries.
Yeah, I'm looking at the chemistry of standard alkaline batteries here.
The modern alkaline battery is essentially just a controlled version of the exact same electrochemical reaction we use to protect steel.
No way. Really?
Yeah. In an AA battery, like the one running your TV remote right now, zinc is the anode. Often it's used in a powdered form inside the battery to maximize the surface area.
Ah, because more surface area means more zinc atoms are instantly available to oxidize and dump their electrons into the circuit.
Exactly. The zinc anode desperately wants to oxidize. So when you turn on your flashlight, you complete the circuit.
You're giving the electrons a bridge.
Right. You're providing a path for those electrons to flow from the zinc anode through your device's electronics and back to the cathode. You are literally powering your devices by harnessing zinc's thermodynamic drive to sacrifice its electrons.
So it's everywhere. It protects our infrastructure, it hardens our plumbing, it powers our electronics, and the manufacturing sector leans heavily on it too, right, for die casting.
Oh, die casting with zinc alloys is crucial for complex manufacturing. Because it flows so beautifully when it's molten, you can cast incredibly intricate, high-precision shapes.
Like automotive gears?
Automotive gears, lock mechanisms, even the tiny interlocking teeth of a zipper. It cools quickly and retains excellent dimensional stability.
Okay, so industrially, zinc is an absolute powerhouse. It facilitates chemical stability in our physical world. But exploring the notes further, there is a thematic pivot here that is absolutely fascinating.
The biological side.
Yes, because that exact same chemical trait, that unique flexibility in handling electrons, is precisely why biological systems adopted zinc billions of years ago.
Yes, this is where the story of element 30 bridges the gap between macroengineering and microbiology.
Here's where it gets really interesting. Zinc is an essential trace element for human health, meaning our bodies cannot synthesize it, right? We have to absorb it through our diet.
Exactly. And if we connect this to the bigger picture, in the same way zinc facilitates stability in a steel bridge, it facilitates stability in our cellular machinery.
Now, when you first hear that, it's hard not to picture, like, tiny galvanized pipes inside our veins.
Right. But it isn't acting as a physical shield in our bodies.
It's acting as a structural linchpin.
That is the perfect way to describe it. Zinc is a required structural component in hundreds of different enzymes and transcription factors.
The sources specifically highlight this structural motif known as zinc fingers. And this honestly blew my mind because it explains how our DNA is actually red.
Zinc fingers are one of the most elegant structures in biology. Proteins need to fold into highly specific, three-dimensional shapes to be able to interact with DNA.
And they can't do that on their own.
Often, no. A zinc ion will bind with specific amino acid residues, usually histidine and cysteine, and it acts like a microscopic knot.
A knot.
Yeah, it pulls the protein chain together and holds it rigidly in a loop, a finger.
And that precise shape allows the protein to physically slot into the major groove of the DNA double helix.
Exactly. Without that single zinc ion anchoring the fold, the protein just unravels. It loses its shape, and suddenly your cells can no longer read the genetic instructions required for DNA synthesis, cell division, protein generation.
So biological growth is entirely dependent on zinc holding those transcription factors together.
From the moment of conception, yes.
It also plays a heavily documented role in immune function. We always hear the colloquial advice to, take a zinc lozenge when a cold comes on.
Right, though we should definitely caution that we aren't giving medical advice or pushing unregulated supplements here.
Of course. But from a strict biochemical perspective, zinc is deeply embedded in how our immune system operates, right?
It is. But it's important to understand the mechanism. Zinc doesn't just broadly, boost the immune system. It acts more like a cellular traffic cop.
How so?
It regulates the production and signaling of cytokines, which are the proteins that tell your immune cells where to go and how aggressively to attack a pathogen.
So it's about moderation. It ensures the immune response is strong enough to clear the infection, but prevents it from overreacting.
Exactly, because overreacting causes excessive inflammation, which can damage our own tissue.
So it is all about biological homeostasis.
Precisely. And that balance is delicate. Because it's a trace element, the body operates within a very narrow optimal window of zinc concentration.
Too little, and enzymes fail to fold properly, leading to compromised immunity.
Right. And stunted cellular growth.
But the sources make it explicitly clear more is not better. If you overload the system with high-dose zinc supplements, it actually becomes toxic.
Because of cellular competition.
What does that mean?
Well, high levels of zinc trigger the body to produce metallothionein, which is a protein that binds to heavy metals. The problem is, this protein also aggressively binds to copper.
Oh, I see.
So if you consume excessive zinc, you effectively block your body's ability to absorb copper, which is another essential trace element required for red blood cell formation and neurological health.
You essentially induce a secondary deficiency? It's a brilliant reminder that biology is this complex, interwoven ecosystem. It's not a simple math equation. You can't just dump more of a raw element into the system and expect a linear upgrade.
Definitely not. But whether we are discussing the extraction of fluorite in a refinery or the binding of histidine residues in a human cell, the thermodynamic laws governing zinc remain absolute.
You know, looking at all of this together, from the suspension bridges to the cellular DNA, there is a really profound philosophical thread running through the science of this material.
How so?
Well, engineering, both human and biological, is fundamentally about managing stress, right? Navigating inevitable decay. We spend so much effort searching for the unbreakable shield, the material that will just never degrade.
The holy grail of construction.
Right. But zinc proves that immense system-preserving value doesn't always come from being invulnerable. It comes from calculated vulnerability.
I love that.
The most important component in a complex system isn't necessarily the one that survives the attack. Sometimes it's the one specifically designed to absorb it.
That is essentially the defining ethos of modern material science. We know we cannot defeat oxygen in time. True engineering is designing for failure.
Designing for failure.
It's anticipating the attack and providing a highly reactive sacrificial pathway so that the core load-bearing structures, whether that's a steel I-beam or a delicate sequence of DNA, remain perfectly intact.
We don't try to stop the fire, we just get to choose exactly what burns.
And zinc is the ultimate expression of that choice. It oxidizes so the iron doesn't have to. It gives up its electrons so our devices can run.
It anchors the protein folds so our genetics can be expressed.
Its entire utility is derived from its willingness to participate in reactions.
It really brings us back to that core mystery we started with today. Why does zinc sacrifice itself to protect steel?
It does it because its standard reduction potential demands it. It is thermodynamically destined to be the anode, and we have simply learned to harness that atomic destiny to build our modern world.
There is a line from our source material today that synthesizes this perfectly. It says, "The periodic table isn't just a table, it's a story of the universe."
That's the beautiful way to phrase it.
It is. It's so easy to look at that chart on a classroom wall and just see a block of letters and numbers. But every single element has a highly specific set of electrochemical rules it must follow.
Right, and those microscopic rules dictate the entire shape, scale, and survival of our macroscopic reality.
Without element 30 willingly acting as the universal electron donor, the towering steel infrastructure of the 21st century simply could not exist.
It really is the invisible protector,
Yeah.
quietly weathering away on the water pipes buried under your street, holding the crystalline structure of the brass keys in your pocket.
And stabilizing the enzymes that are actively reading your DNA at this very second.
It's quite humbling when you think about it.
It really is. So, as you move through your day today, take a look at the physical environment around you. The streetlights you drive under, the galvanized nails holding a fence together, or even just the battery inside your TV remote. Consider the immense amount of energy it took to pull that metal from the earth just so it could silently degrade to protect something else.
It's everywhere, just doing its job.
It makes you wonder, how many other invisible, sacrificial systems are quietly holding your world together right now, entirely unnoticed? It definitely makes you look at the mundane objects around you with a lot more respect.